Alright, if you guys could please turn to Unit 4, Congruent Triangles. I'm going to fill out some definitions for the first two rows. Alright, a triangle is a polygon with three sides. A triangle with vertices A, B, and C is called triangle ABC, like this. This little symbol here is my symbol for triangle. Okay? A scalene triangle has no congruent sides, so all the sides are different. An isosceles triangle has at least two congruent sides. An equilateral triangle has three congruent sides, so all three congruent sides. So if I ask you to classify a triangle by its sides, you're going to tell me it's either scalene, isosceles, or equilateral. Okay? Now, if I ask you to classify a triangle by its angles, an acute triangle has three acute angles, a right triangle has one right angle, an obtuse triangle has one obtuse angle, and an equiangular triangle has three congruent angles. Okay? So frequently you'll find that a question will ask you to classify a triangle by both its sides and its angles, in which case you need to give me one of these labels and one of these labels, so two answers. So you need to be very careful. If they say classify a triangle by its sides, don't give me one of these, or if I say classify a triangle by its angles, don't give me one of these. Make sure you know what the label means before you use it. Also, it is important to notice that an equilateral triangle is also isosceles, and an equiangular triangle is also acute. Alright, the angles inside the triangle are called interior angles. The angles outside a triangle, like when you extend this line here, this angle, this is an exterior angle. Okay? The triangle sum theorem states that the sum of the measures of the interior angles add up to 180 degrees. So this angle, and this angle, no matter what kind of triangle you have, if you add up those three angles together, you're going to get 180 degrees. Okay? A corollary to that states that if you have a right triangle, the acute angles of that right triangle are complementary, which makes sense because the right angle is 90 degrees, so obviously these two angles have to add up to 90 degrees to add up to 180. Okay? The exterior angle theorem states that the measure of an exterior angle, like this one shown, is equal to the sum of the measures of the two non-adjacent interior angles. So, if I were to add angle A and angle B together, I would get something equal to the measure of angle 1. Okay? Alright, what we have here, we have various postulates and theorems that can be used to prove that two triangles are congruent. SSS stands for side, side, side. If you have two triangles and you can prove that all three sides are congruent, you know the triangles are congruent. So for example, in this case, if this side is congruent to this side is congruent to this side, this side is congruent to this side, you know triangle RST has to be congruent to triangle ABC. Okay? If you have two triangles where you have two sides that are congruent and you have an included angle, included means the angle is in between the two congruent sides, SAS states that these two triangles would also be congruent. Alright, hypotenuse leg. This one can only be used for right triangles. So let me write that down. Okay, if you have two right triangles and you have congruent hypotenuses and a congruent leg, the two triangles have to be congruent. ASA, if you have two angles congruent and an included side, once again included means in between the two congruent angles, then you know those two triangles are congruent. I also want to point out, up until now, I've been putting little dashes in the angles. This is another way that you can label the two triangles are congruent. You could just put an arc. So this angle is congruent to this angle, because there's two arcs, would be congruent to this other angle because there's two arcs. Okay? Now, ASA is different from AAS. AAS states that if you have two angles and a non-included angle congruent to two angles and the corresponding non-included angle in another triangle, then those two triangles have to be congruent. It's very easy to get these two confused. Keep in mind that in ASA, the side is in between the two congruent angles, and in AAS, the side is not in between the two congruent angles. All right, this theorem's a little bit different. CPCTC stands for corresponding parts of congruent triangles are congruent. And this basically says that by definition, congruent triangles have congruent corresponding parts. So, if you can prove that two triangles are congruent, you know that their corresponding parts must be congruent as well. So, if I said, hey, I need you to prove that this particular side is congruent to this other particular side, and you know that those two triangles are congruent, then by CPCTC, you know that that one piece of the triangle is congruent also. Alright, now if you guys remember, we've learned that a triangle is isosceles if it has at least two congruent sides, like the triangle shown here. When an isosceles triangle has exactly two congruent sides, these two sides are called the legs. The angle formed by the legs is called the vertex angle. Okay? The third side is the base, and I actually meant to write base here. Let me do that now. Okay? The third side is called, is the base of the isosceles triangle. And the two angles adjacent to the base, so in this case A and C, are called the base angles. So the base angle theorem states that if two sides of a triangle are congruent, then the angles opposite those two sides are also congruent. So in this case, AB is congruent to BC, therefore angle A is congruent to angle C. Okay? The converse of the base angles theorem is basically says that if angle A is congruent to angle C, then AB is congruent to BC. Also, we have these two corollaries. If a triangle is equilateral, then you know it's equiangular. If a triangle is equiangular, then you know it's equilateral. Alright, transformations. A transformation is an operation that moves or changes a geometric figure in some way to produce a new figure. The new figure that it produces is called the image. Alright? A transformation can be shown using an arrow, kind of like this one here. This would be an example of coordinate notation. I was going to talk a little bit about coordinate notation here, but instead I just incorporated it into over here, so you can just leave this blank or doodle or write something else there if you like. There are three main types of transformations. A translation moves every point of a figure the same distance in the same direction. A reflection uses a line of reflection, like one of the axes, to create a mirror image of the original figure. Okay? And a rotation turns a figure about a fixed point. So it just kind of rotates it. Okay? The fixed point it turns it around is called the center of rotation. Now, in a coordinate plane, a translation moves an object, moves an object a given distance right or left and up or down. You can use coordinate notation to describe the translation. For example, this translation shows that the figure is translated horizontally A units and vertically B units. Okay? For this class, when a reflection is shown in a coordinate plane, the line of reflection is always going to be the x-axis or the y-axis. You can actually make different lines of reflection, but for this unit, in this class, we're going to stick to the axes. Okay? If a reflection about the x-axis, you would just multiply the y-coordinate by a -1. A reflection about the y-axis, you would just multiply the x-coordinate by a -1. Okay? Alright, in this lesson, if a rotation is shown in a coordinate plane, the center of rotation is always going to be the origin. Once again, you can have a different center of rotation, but for this unit, for this class, it's going to be the origin. The direction of rotation can either be clockwise or counterclockwise. The angle of rotation is formed by rays drawn from the center of rotation through the corresponding through corresponding points on the original figure and its image. So like for example here, this line follows this side here, and this line follows the corresponding side, and the two lines make a 90-degree angle. That's how you know that this was rotated 90 degrees clockwise. Same thing over here. The drawing is a little bit off, sorry, but it kind of sort of you can tell that it's going counterclockwise. It's supposed to be about 60 degrees. Okay? Notice that rotations preserve, or it's hard to tell in my drawings, but rotations are supposed to preserve distances from the center of rotation. So segments drawn from the center of rotation to corresponding points on the figures are congruent. So this segment is supposed to be congruent to this segment, even though it doesn't look like it because my drawings are off. This segment would be congruent to this segment. All right, and that's all for Unit 4.